Well, first of all, welcome. I know being right after lunch is usually not the best time for doing a presentation, especially not on the last day, but I appreciate you're all here. The title may be a little bit misleading. What I'm going to talk about is not necessarily purely packet core, but a specific part of that. And what I'm going to talk about is what is going on the GI on the GI LAN interface. So that's the interface between the GGSN and your internet peering router. There's a whole range of equipment and solutions out there which are currently being engineered by mobile operators, and there's a lot of evolution in that space. And as a solution architect in F5, I have the pleasure to talk with almost all the mobile operators in Europe, and I get to exchange some ideas and stuff. And what I want to do in the next 30 minutes is really give you a flavor of what are we seeing operators asking in terms of how to optimize that architecture, and second, how can you make it more easy to create new services on that GI LAN? Because at the moment it's a fairly complicated architecture and people want to simplify that to get cost benefits as well as revenue opportunities. So if you take a look at how these networks are looking like today, it's a fairly complex set of different types of equipment. So on the left hand side there, I'm not sure if the pointer works, yep. So you have your GGSNP gateway here, which feeds into a battery of different network elements before you actually go to the internet ecosystem. So examples here, you may have routers and switches for some policy-based routing into a VAS plane, which we'll talk about in a second. You may have DPI platforms there. You typically have a firewall there, the so-called GI firewall. And then if you run out of IPv4 addresses, you typically have some sort of a CGNAT device in there as well. So you see there's a whole range of equipment deployed in a chain, which as you scale the network, you need to scale them one by one, which is one problem. People want some level of simplification there. They want to reduce the number of elements, not necessarily to one single element, but definitely reduce it to a more manageable number. The second challenge that operators are coming to us for is this part. So if you look at things like video optimization, transparent caching, URL filtering, these are typically very, very expensive systems in the end-to-end mobile network. Today, most of the operators have fairly static policies where, for instance, you just forward all port 80 traffic into a video optimizer farm. Same thing is done for transparent caching. So all port 80 traffic goes through it, which means that the majority of your traffic is piped through each of these systems. Now, I'm sure you've all seen market statistics in terms of how bandwidth is going to grow with LTE and how much video you're going to get. So all operators I'm talking to, they are agreeing on one thing, that this is not a sustainable architecture going forward. It doesn't scale. It's very difficult to introduce new services. So people are looking at smarter ways, first to do some level of consolidation at this level, and second, to do some level of offloading of these platforms. Only use them when they add value. Don't just push all your traffic through them. And these are the two things that we're going to talk about. So the first thing is, how do I optimize this type of architecture? So this is really the famous cost revenue curve in the service provider industry. This is really focused on keeping your costs down. And that will very specifically zoom into how do you offload some of these optimization servers and VAS systems on the GI LAN. What people are asking us to do is do some level of what we call intelligent traffic management, or sometimes we call this context-aware traffic steering. What that means is you move away from pure static port 80 forwarding into making a much more granular decision in terms of which packet actually goes to any of these systems you have deployed there in your VAS optimization chain. And context can mean many things. Context can mean a subscriber ID and a policy he has signed up for. Context can mean we need to look deep into the packet to figure out what type of application it is and make a decision based on the application we see. It can go even as far as getting an API into some third-party systems where we get information about congestion levels in the network, and potentially we may take a different steering decision based on how congested that network is. So context can come from the data plane, it can come from the control plane, it can basically come from anywhere, but it's really making a very granular decision in terms of which packets need to be forwarded to that VAS optimization plane. If we take a few examples, video optimization is a very hot topic in the industry these days. Many mobile operators have been deploying video optimization for the sake of saving capacity on the radio network. So by doing transrating and transcoding of video streams, you basically reduce the amount of data you send to the end user. And by doing that, you save capacity on the radio layer. So in some ways, that was sort of a cost saving. Most operators these days are now coming back from the idea of doing this for all traffic. They're coming up with ideas to make it, again, contextual. Some operators are asking us, like, I don't want to send all my HTTP traffic to the video optimizer. I only want to send those HTTP requests which are specifically asking for a video stream. So and if you need to do that, you obviously need to look much deeper into the HTTP layer than just looking at port 80 number, right? So that's something we do in certain cases. Other use cases are with the deployment of LTE, where they say, I want to continue to do video optimization for 2G and 3G, but I don't really want to do it for LTE because I have plenty of capacity, certainly in the beginning. And if you have a converged P gateway, obviously all your traffic comes out of the same gateway. So here again, we need an interface with a control plane that tells us when a user is moving from 2G, 3G, LTE, back and forth. And going even a step further, that's really congestion-based traffic steering. We've been working with third parties in the industry. One of them is Alcatel-Lucent, which have a system that can monitor congestion levels in the radio network. And via an API, they can give us information about which user is in a congested area. And then again, based on that, we can take a different steering decision. So certainly on the video optimization side, it becomes a very hot topic these days, because video optimization is expensive technology. Similar thing is starting to happen for transparent caching. So in transparent caching, again, typically people have been doing port 80 forwarding to a transparent cache. So we have been deployed in those types of environments for many years as part of a load balancing type of architecture. But now more and more people are deploying us in line, where we look deep into the HTTP headers. And then based on a blacklist, whitelist type of approach, we decide which type of HTTP requests we're going to send to a caching server and which ones are going to bypass. A whitelist is done by customers who have a very good idea in terms of which sites do I believe are cacheable and are very popular in my country. The blacklist type of approach is typically deployed when you have, for instance, Google Cache connected straight into your network. In that case, if you deploy a transparent cache right next to it, you may not want to pipe your Google traffic through your own cache, because that's going to be served by the Google cache. So these are examples of transparent caching. Parental control slightly different, because that's more a subscriber opt-in, opt-out service. But here we see that mobile operators in the past have been deploying APNs for doing service separation, right? If they introduce a new service, they create a new APN so that they can isolate subscribers, and then they have VLANs on the GI LAN to manage all that. But the more service combinations you're starting to make, the less appealing that model becomes. And service providers want to go for less APN rather than more APNs. So again, here, a subscriber-based steering approach is a solution that doesn't put any dependencies on your GGSN. It doesn't put any dependencies on the APNs that you need to use. So let's walk through a simple example here. So let's assume we have 3 users. User John has a service policy which specifies that I want to optimize video for user John, but not when he's in LTE coverage. So when he's on LTE, I don't want to do that. User Paul has another example. For him, we're always going to optimize video streams, and he has subscribed himself to a parental control service. So for this user, we need to send this traffic to do different VAS services. So let's focus on these two for the sake of simplicity. So that's a policy that can be stored in a radius database, in a PCRF, which can push down to this intelligent steering device. Also on this side, you see a radius interface. Typically in this type of deployment, we use radius on this side because the GGSN, when it sends out a radius accounting start, it gives us information about subscriber ID, IP address, and RAT type. And most GGSNs can be configured that when a user moves from RAT type, so if you move from 2G, 3G, LTE, they send an interim update. And if they flow through our system here, we can actually record that and take that type of information into account for our steering decision. So we learn information from a PCRF, we learn information from the control plane of the GGSN, and we bundle all that information together to make that steering decision that does what your business policy defines us to do. So if John is sending HTTP traffic over an LTE network, then we're not going to do anything. We're just going to send this traffic straight to the internet because his business policy specifies that for LTE, we're going to bypass video optimization. That same HTTP request coming in over 3G is going to be optimized by the video optimizers because then we're going to take that steering decision. So we modify our steering logic based on all these control plane interactions that we get from the system. If we want to go even a step further, we can say that only video requests need to be steered to the video optimization platform. In that type of model, we wouldn't only send all his HTTP traffic through, but only very selective HTTP requests. If we take the example of user Paul, whether he's on 3G or LTE doesn't matter because we didn't specify for him a specific differentiation on that. So his traffic is going to be service chained through two different systems. So you see here it's contextual traffic steering, but there's also a service chaining component to it. And dependent on what type of services you have deployed here, it can get fairly complex because some VAS services, they change MAC addresses, but they don't touch IP addresses. Some of them, they don't even touch MAC addresses. They're completely transparent. And in order to manage all that from a connection level perspective, it gets fairly complicated. And it's not so easy to do with standard, let's say, packet-based forwarding platforms. Obviously, the goal is really to get to very granular service creation, as well as to get that level of offload on the VAS optimization layer I explained above. Only send traffic through these VAS systems when that VAS system can add value to the traffic. Don't just pipe it through in a serial chain, because that's not economically viable going forward. We've heard about SDN, NFV for sure. I wasn't here yesterday, but I understood Deutsche Telekom presented TerraStream, which obviously is an NFV type of project. So here is a use case of how NFV fits into this type of architecture. And in fact, we have already been doing demos for some customers of this. One of the first technologies that we see moving into an NFV virtual type of environment are these VAS optimization services. Why? Because they're either very CPU intensive or they're very storage intensive. And standard COTS hardware is very good at that. It's not so good yet at the networking level. They're getting there, but at CPU storage perspective, this is the best equipment you can get. So things like video optimization and transparent caches are very good candidates to move in a virtual type of environment. So same environment as before, but now all these optimizer services are living in a virtual world, are managed by an orchestration platform, and we are integrated with that orchestration platform as well. F5 as a company, we obviously have a lot of business in the IT space as well, so we have done integrations already with various orchestration tools, as were discussed this morning as well. And the whole idea of this architecture is that if you have more users on the left-hand side, we steer and load balance traffic through each of these virtual machines. We monitor the consumption level, CPU level, whatever you want to monitor on these virtual machines. And if we measure that we are getting above a certain threshold, we send a signal to the orchestration tool, which will then automatically is going to spin up new virtual machines for whatever service that is required at that point in time. If we measure that traffic goes below a certain threshold, we will give a similar signal to the orchestration tool. He's going to spin down the virtual machines, give them back to the pool. And now you have a fully dynamic environment where video optimization, caching, URL filtering, what have you, automatically adjusts itself in a fully dynamic and agile fashion. So this is a perfect example of an NFV use case that is very real today. So that was the intelligent traffic management, the offloading of the VAS optimization plane. The second thing is the consolidation level. This is something most of you are very familiar with. This is what happened in the routing industry. I used to work for router companies as well before, so I've sort of lived through that transition from dedicated BRASs, MPLS-PEs, peering routers, etc., into what is now called multi-service router, or maybe every routing vendor has its own name for it. But take Juniper, Cisco, Alu, Huawei, they all have a multi-service router, where you no longer look at these things in terms of platforms, but you look at these things in terms of functionalities that you want to run on a routing base platform, so to speak. That transition has happened, and the industry has embraced it, and it's deployed almost anywhere now. What we in F5 are doing is we're actually trying to do the same thing at layer 4, layer 7 level. So especially on the GI LAN, people are using proxies for HTTP header enrichment, WAP gateways, what have you. They're using DPI technology to look very deep into the packets. That's a layer 7 function. They deploy firewalls and CGNATs, which in that portion of the network is very much a layer 4 function. They use some steering capabilities, which are either very static or very dynamic, as I explained before, which can be, again, layer 4 or layer 7. So all of these functionalities sit somewhere at layer 4 to layer 7 of the OSI stack. And what we in F5 are doing is we are actually implementing all these things on one single common base. And I'll show you later on why that presents significant benefits. So essentially, on top of this intelligent traffic management that I walked you through, we are also embedding some of those functions which were sitting here, right? The DPI platform, which gives you that per subscriber DPI capabilities, detect peer-to-peer, Skype, those types of things, over-the-top applications, the GI firewall for the security part, and the CGNAT as well. Of course, everything, you can talk as much about functionality as you want. The scalability and the performance needs to be there as well, right? So we do meet those scalability requirements as well. Otherwise, it wouldn't make much sense to do so. So on the DPI side, yeah, I think I don't need to go through the details of this. I think everybody here in the room is very familiar with what DPI platforms are about. But we do add a couple of other things like TCP optimization, header enrichment, WAP offload to the systems. CGNAT and IPv6 transition. I think most of these technologies speak for itself. And then network security, so that's the GI firewall. That's also an area where we see a lot of mobile operators struggling because not so much on the bandwidth side, but on the number of connections, number of simultaneous connections that you can hold in your forwarding table from a security perspective. And again, that's a parameter where we have very high numbers on. So that's the optimized part. So let's talk a bit about monetize. What do we see happening in the market in terms of what type of services people want to start creating on these networks? I would boil them down into 3 broad categories. It's quality of experience management. So this is anything related to bandwidth control, optimizing TCP, traffic steering to video optimizers falls into that category to a certain degree. It's the opt-in, opt-out model where you as a service provider have different types of services that you offer to your end users, and you want to give your end users the ability to mix and match in whatever way they want. So that requires some tools in the network to make that easily feasible. And then anything related with the over-the-top players. I think over the last 10 years, service providers have been trying to fight the over-the-top players. I've seen a very significant change in that in the last 6 to 9 months, I would say, where I see several service providers now teaming up with some of the OTT players to make a bundled solution. So that's quite an interesting evolution as well. On the bandwidth control, I would say I haven't seen it that much yet. Some operators are starting to trial this. Of course, in the fixed world, this is a very common thing to do, sell packages based on bandwidth. In the mobile industry, it hasn't been done so much yet. I've seen some operators thinking about it for LTE, because with LTE, the risk is that if you only have a few users on LTE, you give everybody a mind-blowing experience on day one, which is only going to get worse the more subscribers you get attracted to your network. So in order to control that a bit, some people are playing with the idea of providing some level of per subscriber control. I already spoke about the steering to video optimizers and transparent caches. To a certain degree, that's a cost-saving element. To another degree, that's a subscriber experience management tool. But also TCP optimization has proven to give service providers a lot of gain. So just by being a TCP proxy in the network and by playing a different protocol stack on the radio side versus on the internet side, which are completely different in terms of characteristics, delay, packet loss, etc., by playing on those sites, you can get significant savings. We have a large tier 1 operator in Europe which claimed that they have saved more than 20% on their radio layer by implementing TCP optimization. And that's a business case in its own right, really, if you get those types of savings. Opt-in, opt-out, value-added services. Actually, this sort of reflects back to what I was explaining in terms of the service chaining. So on a per subscriber basis, a policy is going to define how you're going to steer traffic for each and every customer individually. So no matter how many services you add to the mix, it's going to be very easy to manage if you have a central intelligent traffic management platform that can orchestrate all that from one single point. And then the monetization. So this is an interesting one. There's quite a few operators now who already have bundles with music streaming services. Spotify being a very popular one. Deezer in some countries is popular too. So what they've been doing is they've been adding a subscription to an over-the-top music streaming service into the local mobile subscription. And usually they do it for a slightly smaller fee than what you would buy if you go directly to Spotify and Deezer. So it's a bit of a win-win because they get a few more customers by doing that. And for the mobile operator, if your customer is hooked up on Spotify as a service, they're unlikely to move away from you. So it's a sort of a stickiness creation, if you will. Now, of course, what they want to do is if you have such a Spotify streaming service, you want to take that streaming service out of your volume cap. So now you need some sort of a DPI engine that figures out if traffic for a particular subscriber is Spotify. If yes, I'm going to take it out of his volume cap because you don't want that service to interfere with the volume cap that you're selling. The other thing that some operators are thinking about is providing an end-to-end QoS guaranteed service. So what we would have to do in this case, if we would not only have to take it out of the volume cap, but we also have to give it a diffserv code point marking so that the GGSN and P gateway can treat that diffserv code point as a way to map the traffic into a dedicated bearer which has a higher QoS on the LTE network. And the reason being that with LTE, customers or mobile operators will have to invest in the QoS technology anyway for VoLTE. So while they are going through that exercise, they're starting to think like, if I need to do QoS for VoLTE, can I not use the same technology for a guaranteed over-the-top service? So these are things, nobody has rolled this out yet, but these are things that I'm starting to hear in the industry with some concrete plans. Monetizing the subscriber relationship is another element. This is about, sometimes you go to a service provider and they say like, you know what, Google and Facebook, they know so much more about my customers than I do. Whereas in fact, the mobile operator does have some knowledge about subscriber and he can gain a lot of knowledge from that subscriber if he wanted to. So there are already some use cases. HTTP header enrichment is a very popular one where you add the mobile subscription ID into an HTTP header so you can do a mobile payment service. There's also use cases for advertising agencies, so that the service provider which has the knowledge about the subscriber is going to sell that knowledge to an advertising agency so that the advertising agency can be more specific in what type of advertisements you're going to send to that user. And the thing is, if you look at all these things, the intelligent traffic management, these monetization aspects, if people are convinced that they're going to deploy this, then they are deploying some system in their network which has all that knowledge. You have the knowledge about the subscriber, the applications he's going to, what he subscribed to. We know about all these things, because we have all these control plane interactions, data plane interactions, that information is all there to take that intelligent decision on what to do with the packet. So why not export it and populate a big data database? Now you have much more information than you had ever before, and you can start exploiting that in a much more smart fashion than was ever done before. So this opens up a new opportunity, really. Now, talking about intelligent traffic steering, all the monetization aspects, what is required from a technical perspective in the network? Very quickly. On the control plane side, radius for discovering the subscriber, so that's the interaction with the GGSNP gateway. This gives us a lot of information about the user, what type of radio network it is. We can identify whether he's a roamer or not. Diameter GX, obviously, for policy control, but nothing prevents you from pushing policies down using other interfaces. We have customers doing it with radius. We have customers doing it with LDAP. So there is some flexibility built into the product to make that adaptable to any type of situation you may have. And then, of course, syslog for all the reporting, for getting the feed out to a big data system, as an example. And then GY for any type of charging interfaces that you want to do. In terms of the packet classification, so when traffic flows through our box, what do we need to know? We need to know who the subscriber is, the device type, we can figure out what it is, the application, our DPI inspection engine will figure out what the application is. We can build APIs to get information about network awareness, congestion levels. And we also have an IP reputation database, so we can figure out if IP addresses are coming from botnets, malware, and all that stuff. And all that can be combined into a policy, and that policy will then determine what are you going to do? What is the enforcement action that you're going to do? And this is just a recap of all the use cases I explained, right? Traffic steering, service chaining, reporting, QoS marking, bandwidth control, basically all these capabilities. So it's very rich classification, data plane, control plane, and then a lot of manipulations at the data plane level. This is what I wanted to talk about in terms of the benefits of consolidating. If you have a series of layer 4 to layer 7 devices deployed one after the other, then each of these devices have to go through a fairly expensive CPU operation to go all the way up the protocol stack, do whatever they need to do, and then go down, push it back on the Ethernet wire, and then we go up and down again. What we do is we actually go up the stack on the user side. We inject whatever type of functionalities you want at each of these layers. Then we take potentially, if you wanted to, a contextual steering decision where we feed all sorts of context into it, and then we walk down the stack again and plug in any type of functionality you want. So if you do firewalling and DPI, it's not like we go up the stack, we do DPI, and then we go up the stack again to do firewalling. No, we go up the stack once, and we plug in our functionalities at each level of what is required. So to sum up, this is what we see now as the new GI LAN. It's significant amount of reduction of platforms here, consolidate that into a single platform, and then having the control plane interfaces to make much smarter decisions in terms of which packets are going to which VAS and optimization platform. And with that, I would like to thank you for your attention.